So today I want to talk about functors in Haskell. And functors are represented as a type class where a parameterized type f can become an instance of the type class if it provides a method fmap, which given a function of from a to b and an object of type fa produces an object of type fb. So intuitively, functors are kind of like a wrapping structure. They wrap objects, but through fmap, we can still get at the underlying objects. In particular, we can apply functions to the underlying objects, but still keep them wrapped inside the functor. The important thing with functors is that they satisfy the two functor laws. So the first functor law says that fmap preserves the identity. The second functor law says that fmap respects composition. So in the sense that fmap of f composed with g is the same as fmap of f after fmap of g. Next, I wanted to go over a simple example of a functor. So for this example, we're going to use list. Here I've built as a list type, list of a, which is either nil or a cons of a with list of a. And I'm just driving show for simplicity to show in the interpreter. Now we're going to make list an instance of the functor type class. And so that means we have to define fmap. So when we have nil, of course we just return nil. There's nothing to do. In the case that we actually have a cons of x and some x's, well, we'll just apply f to the head of the list and then recursively call fmap on the rest of the list. So just to see how fmap can work, we have this list L1, which is just the list 1, 2, 3, and then we can use fmap to increment all elements of the list. So here over on the left, I'll load this example, and then we can see L1 is the list 1, 2, 3, and L2 is the list 2, 3, 4. So fmap has incremented every element of the list L1. So next, I actually, with this example functor, I actually want to prove the two functor laws. So remember, the first functor law said that fmap preserves the identity, and the second functor law says that fmap respects composition. So I'm going to go back to whiteboard for that. All right, so we're back to whiteboard, and I wanted to now prove the two functor laws for the list functor we defined. So here I've just copied the definition, so we have it for reference during the proofs. So remember, the first functor law is that the fmap respects the identity, but one thing to note here is that the two identity functions here have two types. So one has type a to a, while the other has type list a to list a. So for our proof, let's just make this explicit, and we'll do id a for the identity on a, and id l for the identity on list. Okay, so for this functor law, we want to prove that fmap of identity on a is the identity on list. Okay, so that's just the claim stating again the functor law. So fmap of the identity of a is equal to the identity of l. So for this proof, what we're going to actually show is that fmap identity of a applied to any x's gives us x's for any x's of type list of a. And because the list is built inductively, we're going to show this by induction on the form of the x's. So in the base case, we'll just assume that x's is just nil. Now this case is pretty obvious. So fmap id a of x's, well, it's nil by the first line of the definition of fmap. And we just continue this string of equalities. Well, x is nil, and that's the same thing that the identity on list would produce for x's. So the base case is done. Now we move on to the inductive step. So in this case, we're going to assume that x's is of the form cons y and y's. And our inductive hypothesis is that fmap, we've already proven the statement for the y's. So fmap identity on A of y's is y's. Okay. So let's just kind of compute this. So fmap identity on A of x's. Well, let's just go by the definition on 2, the second line of the definition of fmap. This is cons identity on A of y, and then fmap f of y's. Well, the identity on A on y is just y, so that works out fine. And then here is where we're using that induction hypothesis. So fmap of fmap f and y's is actually just y's by the induction hypothesis, right? And well, cons y y's is what x's is. So using induction, we've shown that fmap identity on A of x's is x's. So we proven the first functor law. Now let's move on to the next one. Okay, so for this functor law, we want to show that fmap respects composition. So for this, again, we're going to kind of follow the same strategy. So we're going to apply, actually use a list, an element of list called x's, and we're going to show that fmap f after g of x's is the same as fmap of f composed with fmap of g of x's. And we're again going to use induction on the x's. So first, let's start with the base case. So x's, assume x's is nil. And we're just going to, again, compute in a string of equalities. For convenience, we'll start with the right-hand side of the equality, and then end up deriving the left-hand side. So fmap of f composed with fmap of g applied to x's. So let's just first associate. So that means that we apply fmap g of x's first. Well, x's is nil, so by 1 of the definition of fmap, this is just going to be nil. So now we're applying fmap of f to nil, and again by 1, that's just going to be nil. Well, nil is also equal to fmap of f dot g of x's. Again, because x is nil, if we do fmap with any function applied to nil, we're just going to get nil, and that's by 1. Let's move on to the inductive step. All right, so in the inductive step, same strategy as last time. We'll say x's is of the form cons y y's, and we've already shown it for y's, so that means fmap of f composed with g of y's is the same as fmap of f composed with fmap of g of y's. Again, it's more convenient to start with the right-hand side of the equality, so let's do that. So we'll just use the definition of composition. So we retain the fmap of f, and then we're going to apply fmap of g to the x's. So this is just the second line of the definition of fmap. We get cons g applied to y, applied to the head, and then fmap of g applied to the tail. So now we're going to fmap f onto this list, this cons. So we're going to get cons of f of g of y, and then fmap of f of fmap of g of y's. Okay, just by, again, this is by the second line of the definition of fmap. Now, we can do some simplification. So fmap of g of y, well, that's just the composition, f composed with g applied to y. So that simplifies there. And we do the same simplification into composition here. And now here is where, in the next line, we get to use the induction hypothesis. So we have fmap of f composed with fmap of g applied to y's. Well, by the induction hypothesis, this is the same thing as fmap of f composed with g applied to y's. So here we get to use our induction hypothesis. And then now let's just unwrap this definition. We have f composed with g in both places. Well, this is just the definition, line 2 of the definition of fmap. So we get fmap of f composed with g applied to y's. So that proves the second functor law. So we've shown that our list definition and the definition of fmap is correct with respect to the functor laws. So thanks for watching.